Myself, Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Aveda Inamdar, Senior College. Now, in the paper Discrete Mathematics, now we start with Unit 4, that is Recurrence Relations. Now, first see what is the definition of recurrence relation. A recurrence relation for the sequence AR is an equation expressing AR in terms of one or more of A0, A1, A2, AR minus 1 for all integers R greater than or equal to R0, where R0 is a non-negative integers. So, what is a recurrence relation C? Here, if we are considering one sequence A0, A1, A2, A3 and so on, then in general rth term we are expressing in terms of previous terms A0, A1, A2, AR minus 1 for all integers are greater than or equal to R0, where R0 is a non-negative integer. To define a sequence corresponding to recurrence relation, it requires to know first few terms, which are called as initial conditions of recurrence relation. It means by knowing the first few terms and using that relation for AR, we can find all the terms of that sequence. For example, consider this sequence 2, 5, 8, 11, 14, 17 and so on. So by observing this sequence, we can immediately say what is the next term, because here every term is obtained from previous term by adding 3. See, 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11 and so on. So in this way, the next term will be 17 plus 3, 20. After that, we get 20 plus 3, 23, like that. So every term is obtained by adding 3 in the previous term. So what we need to write the recurrence relation, it is nothing but previous term plus 3. But while adding that 3 in the previous term, we must know what is the starting element of that sequence, which is 2, because once we know the first term, then we can add 3 in it, then we get the second term, then in second term we can add 3, then we get the third term, like that. So in this way we can find any term of the sequence, but to add 3 in that term we need first term, and so here first term must be given, that is called as the initial condition of the recurrence relation. So how can we write finally the recurrence relation? As A0 is 2, A1 is 5, equal to A0 plus 3, A2 is A1 plus 3 and so on. In general, we write AR equal to AR minus 1 plus 3. So AR minus 1 is the term previous to AR, and in that term we are adding 3. Now from which term onwards we can find the terms? So this is from second term, but we are giving numbering like A0, A1, A2, A3 and so on. So this is for R is equal to 1, 2, 3, 4 and so on, and A0 is equal to 2, that is the initial condition. So once we have given A0 equal to 2 and this recurrence relation, then we can find all the terms A1, A2, A3, A4 and so on. So this is the recurrence relation. Now, see the second sequence. Consider the Fibonacci sequence. This is very famous sequence. After that, we will see what is Fibonacci problem. Now, consider the Fibonacci sequence 1, 1, 2, 3, 5, 8, 13, 21 and so on. Now, by observing the terms of the sequence, it is quite difficult to find the next term, because here first and second term both are same. Now, after 1 we are getting 2 means 1 is added. After 2 we are getting 3 means 1 is added. But after that 2 is added, then 3 is added, then 5 is added. So it is not like previous recurrence or previous sequence in which 3 is added to previous term. So difference was same in that case, but here it is not same. Now observe the sequence carefully. What actually we are doing? See, first and second term addition, we are getting 2. Then addition of second, third term, 1 plus 2 is 3. Then 2 plus 3 is 5. Then 3 plus 5 is 8. Then 5 plus 8 is 13. Like that. It means every term is obtained from previous two terms by taking their addition. Means to find any term we need previous two terms. So if we are given first and second term of that sequence, then third term can be obtained by adding first and second term. Once we get third term, then adding second and third term, we get fourth term. And in this way, we can find any term of the sequence. Now see, if we consider the terms of that sequence as A0, A1, A2, A3, A4 and so on, then we can write all the terms as A0 is 1, A1 is 1, A2 is equal to 2, which is A1 plus A0. A3 is equal to A2 plus A1, A4 is equal to A3 plus A2 and so on. So in general, AR is equal to AR minus 1 plus AR minus 2 for all R greater than or equal to 2. Means 2, 3, 4, 5 and so on. Because AR depends on previous two terms. So A0, A1 must be given. Then we can find all terms from A2. So initial conditions are nothing but A0 and A1 values. So A0 equal to 1 and A1 is equal to 1. These are the initial conditions. So this is the recurrence relation for Fibonacci sequence. Now, these are some examples in which we have to form the recurrence relation. Now see first example. A person climbs a staircase by climbing either two steps in a single stride or only one step in a single stride. Find the recurrence relation for the number of ways of climbing R stairs. First see, suppose there are R stairs in that staircase. Now the condition is that person can climb either two steps in a single stride or he can climb only one step in a single stride. So in this way, if he is climbing the stairs, then how many ways are there to climb the R stairs? So for this we have to form the recurrence relation. Now first we consider AR as the number of ways of climbing R stairs. It means if R equal to 10, then A10 is actually number of ways of climbing 10 stairs. If R is equal to 15, then A15 is nothing but number of ways of climbing 15 stairs. Now in this case we cannot take a naught because if it is a staircase then it must have at least one stair. So we start with r is equal to 1. Now r is equal to 1 means only one stair. So there is only one way to climb one stair. So one step in a single stride, that is the only way. So a1 is equal to 1. Now see, r is equal to 2. It means there are two stairs. Then how can he climb? So we find out different ways. Now see, one way is that only one step in a single stride. So first he will go to first step, then second step. So that is one way. So first, then second, it means it is 1 comma 1. That is one way of climbing that two stairs. Otherwise, it is given that he can climb two steps in a single stride. So directly on the second step. So it is written in this way. Now there is no other way of climbing that two stairs. So number of ways are 1, 1, that is 2. So we can write A2 equal to 2. See why we are writing all this part, because once you calculate for first few terms, then you will get some idea what will be the recurrence relation. So to get that idea, we are finding the first few terms like A1, A2, A3. Now if R equal to 3, so there are 3 stairs now. Now see what are the different ways to climb that 3 stairs. Now the first way is he will go on first step, then second step and then third step, which is written as 1 comma 1 comma 1. Another way he will go on first step and then directly on the third step. So 1 and after that climbing two steps in a single stride. It means 1 comma 2. Another way is directly first he will climb two steps in a single stride. That means he will go on second step and after that one step in a single stride. So it is 2 comma 1. So one step at a time, then 1 and then 2, or 2 and then 1. So these are three different ways to climb three stairs. So A3 equal to 3. Now in general, how can we find a number AR. Now see, the person can reach rth stair from either r minus 1 stair or from r minus 2th stair. See, what is this logic? It is given that he can climb either 2 steps in a single stride or only 1 step in a single stride. So to reach on the r stair, he must reach on the r minus 1 stair so that he can climb 1 stair, or he must reach on the r minus 2th stair so that he can climb remaining 2 steps in a single stride. So r stair he can reach from either r minus 1 stair or from r minus 2th stair. But to climb that r minus 1 stair, how many ways are there? It is ar minus 1 according to our definition of ar. Similarly, how many ways are there to climb that r minus 2 stairs in the given way? It is ar minus 2. So these are either or and there are no ways common. So by some rule or addition principle, total number of ways of climbing r stairs is addition of these ways, that is ar minus 1 plus ar minus 2. Now here again the value of ar depends on previous two terms. It means if first and second term is given, then third term onwards we can find all the terms in that sequence. So the condition on r is greater than or equal to 3. It means we can find from a3 onwards all the terms. But for that a1 and a2 must be given, which we have calculated. So a1 is 1 and a2 is equal to 2. So from a1 a2 we can find a3. Once we get a3, from a2 a3 we can find a4 and so on. So the recurrence relation is ar is ar minus 1 plus ar minus 2 for r greater than or equal to 3. Now see the second example. Derive the recurrence relation for the number of strings of length n using the bits 0 and 1 having no consecutive zeros. Now here we have to form the string of length n using the bits 0 and 1. So we cannot use any other digit here, only 0 and 1. But the condition is that there should not be consecutive zeros. Now let n denote the number of strings of length n having no consecutive zeros and using the bits 0 and 1. Now by hypothesis, these strings do not contain the pattern 0, 0 because consecutive zeros are not allowed. So before 0, 1 should be there and after 0, 1 should be there. If it is a string of length 3 or more than that, but 2 consecutive zeros are not allowed. Now similar to previous case, first we find few terms of that sequence. Now it is a1. Again we cannot take a0 because it is a string of length n, so length must be at least 1. Now a1 means number of strings of length 1. Now length 1 means there is only one place which we have to fill either by 1 or 0. So 1, that is one bit string, or 0, that is another string of length 1. So how many strings are there? 2. So a1 is equal to 2. Now same way we calculate a2. a2 is number of strings of length 2 having no consecutive zeros. So we have to fill two places using 0 and 1 but having no consecutive zeros. So in how many ways we can do that? See, the ways are 1, 1, 1, 0, 0, 1. We can't take 0, 0 as consecutive zeros are not allowed. So there are three ways of forming that string of length 2 using 0, 1 having no consecutive zeros. So A2 is equal to 3. We count these strings according to the number of leading zeros which are k in number. So leading zeros are nothing but the consecutive zeros in the starting. Now case 1, k equal to 0. Now k is equal to 0 means there are no leading 0 in the string. It means string is not starting with 0. So if it is not starting with 0, then the string will start with 1. Now, as we are forming a string of length 1, already the first place is filled by 1. So, remaining n minus 1 places we have to fill by using 0 and 1 without consecutive zeros. So, by definition of n, that is nothing but an minus 1. That means there are an minus 1 ways of forming a string of length n minus 1 using 0, 1 without consecutive zeros. Now case 2, k equal to 1. Now k is equal to 1 means leading zeros are 1 in number. Now leading zeros means number of starting zeros. So k equal to 1 means string will start with 0. Now as string is starting with 0, after that 0, 1 must be there because consecutive zeros are not allowed. So if one leading zero is there, then such string begins with 0, 1 by hypothesis. Now already we have filled 2 places out of n places. So n minus 2 places are remaining, which again we have to fill by using 0 and 1 and without consecutive zeros. So how many ways are there to form a string of length n minus 2? Using 0 and 1 without consecutive zeros, that is n minus 2 in number. Now see, cases k equal to 2, 3, 4 and so on are impossible. Why? Because if k is equal to 2, it means number of leading zeros are 2 in number. That means the string will start with two consecutive zeros, which is not allowed. Same thing happens if k equal to 3, 4 and so on. So the cases k equal to 2, 3, 4 and so on are impossible by hypothesis. So either case 1 will be there or case 2 will be there. Now here all the strings are starting with all the strings are starting with 1, and in second case all the strings are starting with 0, 1. So nothing is common. So how many total ways are there of forming a string of length n satisfying given conditions? By some rule or addition principle, the answer is n is equal to n minus 1 plus n minus 2. Again, if you observe here, n depends on previous two terms. So from third term onwards, we can find all the terms if first and second term is given. So condition on n is n greater than or equal to 3. And the first and second term values must be known. Then only we can find all the terms from A3 onwards. So A1 is 2, A2 is 3. These are the initial conditions. So this is the recurrence relation.